so far we have discussed so many things related to the retrosynthesis, and also we have discussed about the rules, how we can understand the orientation possibility, how the nucleophiles will come, and also the order of events which is can be applied in order to synthesize the various drug molecules. So now today we will start with the, even though we have also discussed the one group disconnections, where we can just leave the one side of the molecule and we can generate the product. So including the two group also, one difunctionalized compound, so where the two functionalized difunctions are present in the same center can be cleaved in order to form the products. 1,2 difunctional, of course the 1 and 2 position having the different functional group can be cleaved in order to finalize the products. 1,3 also is there. So these are the examples where we can break the molecules in such a way that where we can generate various synthons. And of course, synthons are equivalent to the synthetic equivalents. And now today we start with the stereoselective in the organic synthesis. So specifically, selective organic transformation is a condition where we are selecting or we are giving a specific condition to the reaction where it will generate the different products. So in the first terminology, so stereospecific reactions. So in stereospecific reactions, what happens? We are getting the product, of course. Every reaction will get the product. But the thing is that the stereochemistry of the starting material will determine the stereochemistry of the product. So the stereochemistry which is present in the same position will appear in the product. So there will be no change in the stereochemistry. And this is the unique thing for the stereospecific reactions, where there will be no choice of change of the stereochemistry. So usually retention of stereochemistry takes place in this case, but not inversion. So that's why the stereospecific reactions comes under the condition where the starting material has to be transformed to the product with the same stereochemistry, and that is what we call it as stereospecific reactions. And stereoselective reactions is a kind of reaction where the one stereoisomer specifically of the product is major one, preferentially over other. So it is formed. So of course we get the two products in this one. So but one will predominate. So that's what the selectivity is appears. Once we know the selectivity, we can make sure the product which are going to generate via the reaction, it will, of course, it can generate more than two also, but one will get predominant. And this is what we call it as stereoselective reactions. Third one is the diastereoselective reactions, and usually diastereoselective and enantioselective both are very similar one. In this one, diastereomer will be formed, and in this one, enantiomer will be formed. And through the way where it will generate the mixture of products. You see the mixture of products. So two products always it will generate. Nowadays, it may have the amount of the product may be higher for one and maybe lower for one. The concept is that it produces the two enantiomer here and it produces the two diastereomers here with the unequal amount. Of course, it will not have the, if it is equal amount, we usually call it as racemic mixture. So if it is in unequal, something like 91.5% for this one by the addition of phenyl magnesium bromide over the ketones. It is because ketones usually have, we have seen the stereochemistry, ketones will have the two sides. Via the Cram's rules also we have discussed, so the Franklin rule also there. So based on the stereochemistry, we can have the two possible site attacks, and that one which will generate the front side phenyl group and also the back side phenyl group. But usually front side is much more preferred since the phenyl, other phenyl group which is present at the alpha carbon is next, it is in the back side, and that's why the front side is more preferable. In this case, by using dimethyl zinc and DIAB, the -1, it will generate the enantiomers. So S enantiomer and R enantiomer. So this is the DIAB. So -1, and this is the one ligand we can consider as a ligand. So this will determine the stereochemistry of the one of the isomer will be in the highest possible product. So because of this one, and this is what we have the product. You see the dimethyl zinc means this is the source of methyl group, and methyl group is now in the Carbanian way, it will attack at the aldehyde position. Same what we have discussed here, it will have the two possible attacks. So in this case, what happens? A methyl group is present in the plane only. You see both sides. And the thing is that the position of hydroxyl group is changed after the attack of the methyl group. So that means one of the methyl group, both methyl group of course is attaching at the same position, but only the difference is that the stereochemistry of the hydroxyl group is different, and that's what it comes under the enantioselective reactions. So these are just the brief details of how the stereoselectivity is achieved in the organic synthesis. Next is that the stereoselective and the stereospecific reactions. So if we are treating the 2-butene with the bromine, so we will get the dibromo compound. This is very simple reaction. So while the formation of the dibromo compound, there is a possibility of formation of two geometric isomers, cis and trans, and there is also a possibility of three stereoisomers which contains the meso one also there. So if we are treating the trans one, because here we have the two different methyl group on one side, and if it is cis, of course everybody knows we have the same side. So trans one will generate the meso compound, where the product which can be separated via the center of symmetry, and where the two sides of the molecules are in equal amount. जैसे इसका जो रहेगा इसका मेरे रवि अगर हम सेंटर से लेंगे तो दिस विल बी वेरी सेम एंड दिस विल बी वेरी सेम. दिस काइंड ऑफ कंपाउंड कम्स अंडर द meso compound. And for bromination of the cis one, it will generate the different distereomers. And that's what we call it as a stereoselective and stereospecific reactions for this kind of compounds reactions. So now specific more examples is there disulfide reaction. Specifically, when the dinophile is respect to the dine, nophile is respect to the olefin or alkene which is present in the starting material, and if we have the electron withdrawing group there, and this will have the activation energy so that it will activate the dinophile so that we will go to react with the dine fast, and that's why the rate of the electron donating group is less, the rate of reaction. Once we have only one group, of course it is little more, and if we have two groups in on the dinophile, we have the highest one. So that's why the slow it is having reflected for the electron donating compounds, and this is for the electron withdrawing compounds. And that's why the main reason is that इलेक्ट्रॉन विड्रॉइंग ग्रुप जब रहता है वहाँ पे, तो वो क्या करता है, जो लूमो एनर्जी रहता है ना, वहाँ पे वो रिड्यूस कर देता है ना. LUMO in the sense the lowest unoccupied molecular orbital. There will be a HOMO concept is also there. If you look at the orbital theory, you can understand how it is HOMO and LUMO. So HOMO is reflected for the highest occupied molecular orbital, where the molecular orbital will be having the highest electron density in this case. But in this for these reactions in LUMO, having the lowest unoccupied, so there will be a low unoccupied p orbital available which does not have any kind of electron, and that's what, because of this one, why this is happening, so because of the electron withdrawing groups. So electron withdrawing group withdrawing the electron density towards itself in such a way that the molecular orbital it becomes in LUMO it becomes electron deficient, and that's why the orbital which are present on the nearby carbon atoms, it is now considered as a LUMO, and this is playing a key role in order to activate the reaction towards the electron dino with the dynes, because electron this is the dinophile which does not have the electron density much higher in this case, so it will immediately goes to react with this one in concerted mechanistic pathway, and it will generate the products. So this comes under the stereospecific reaction. One more example is given. So if we have, this is the cis one, and this is of course the trans one. So if we have trans, of course the trans product will be formed, and this is the cis, if it is cis product will be formed. So this is also comes under the stereospecific reaction. Of course, we can also go ahead for the bicyclic ring generation, where we can use the anhydride type of dinophile. So this kind of dinophile will already have the fixed conformation. So in previous case, there will be two different conformations where we can have the cis and in the trans also, because it was the open chain form. But once we come to the cyclic form, it will have the fixed conformation. So what actually it may happen, depending on the substituent present on the dynes. You see this is what. So 1,4 position now it looks like axial one, methyl diaxial. So it will go back. There are some rules also there in order to detect in pericyclic reactions how we can understand the product which will where the methyl group will be situated. So in this one it will go back. So if we are having the equatorial one, and that's why it will comes in the front side. So this will generate the product where it is also comes under the series specific reactions. Chemoselectivity is another term where we can be used in the retrosynthetic analysis. And in this one, what happens is that there are several issues related to the chemoselectivity. Because in chemoselectivity, if the relative reactivity of the two different functional groups are there, you see, that alcohol is also there, amine is also there. So the property for the acylation, there will be a possibility of acylation of alcohol also, and there will be possibility of acylation of amine, because the properties of amine and alcohol in aromatic system which is present at the para-para position is very equivalent. So there is a very slight difference in between these two, and we need to make sure whether the acylation group will be goes to which side, and that's why the reason is that acetic anhydride is used here. Under the acidic condition it will go to the amine side, but under basic condition what happens, it will go to the both side, this side also and this side, and it may there will be a possibility of generation of mixture of compounds under basic condition. And that's why the in chemoselectivity we need to make sure the functional group reactivity pattern of the two different group which is having the equivalent reactivity pattern. And this is what is the first concern for the chemoselectivity. Second is that if we have the one of the two identical functional group, then also it will have a problem, because if the product which contains only one methoxy group here, you see, but we have the two hydroxyl group, and we want to do the methylation by using this, by in presence of methyl iodide. So the thing is that the properties of one functional group present at one side of alcohol and this other side will be 100% similar. You cannot differentiate it now. Here you can differentiate it on the basis of acidic and basic condition. Why? Because we have the nitrogen moiety here and here we have the oxygen moiety. And via the electronegativity effect, we can make sure the slight difference in the electronegativity might affect the reactivity pattern of that the functional group towards the acidic condition and towards the basic condition. But in this case we cannot differentiate it, and that's why there will be a difficulty in order to form the only one. So how we can control it? So there is the best way is that if we are using 100 molecules of 1,4-diol, then just use the 100 molecules of base and 100 molecules of methyl iodide. I am just explaining in simple way. Actually it has to be counted by the equivalent of the compounds. So if we are treating these three by controlling the amount, so what will happen? Only one side hydroxyl group get methylated and we get the expected product in major amount. And this is the way how you can control the chemoselectivity by differentiating on the basis of amount of nucleophiles, base and electrophiles to be provided. Next is that the reaction of a group that may react again. So what happens here, if we are treating the thiol group with alkyl bromide, of course thiol will be inserted, and later on what happens, this thiol again it will react with this one. So that's why the group which are present in the starting material may react again. So you must have to overcome the situation where it should not go further. So because once we are generating one product, it should be stable enough. And if we are generating the unstable one, now you see this, there is a minus charge. And if you don't stabilize this minus charge by providing a acidic condition or water, the reaction will get further until it will form the alkylated product. And this is what the concern for the chemoselectivity, where we are treating two different compounds, of course, and after formation of first one, until we get it stabilized by the external force, it will go to the further reactions. And that's what this is also one concern for the chemoselectivity. And there are several guidelines also, so 5 to 6 guidelines are also G1 for the chemoselectivity. This was just the basic some details. Now we will discuss more about the guidelines, the specific guidelines. Now you see the already we have discussed this one. These are the issues already we have discussed, but the same thing will be applied with the more examples. I don't know why they have given paracetamol everywhere. Anyway, just try to understand. So when the first one is that when two groups are in unequal reactivity, you see unequal reactivity, the more reactive can be made to react alone. So जब यहाँ पे अलग दो अलग रहते हैं, of course there are very similar reactivity patterns are available, but even though we can make the amine only get reacted via the acidic condition. So that's what it is explaining the first rule, that if we have two groups which are very similar to the each other in case of properties, but even though we are able to activate only one, and that's what the first rule is. So of course this has already we have discussed, from phenol we can get the nitro, this could be generated from the, this will be transferred to form the amine and then acylation. So this is simple step, nitration, then reduction, and then acylation. But here acylation should be in the under acidic condition. They must have to mention here acidic condition. If you go for the basic condition, of course you get the two product where which we will have the another acyl group in the oxygen position. Next is that second rule is that when we have the functional group may react twice. The reaction is successful only when the first product is less reactive than the starting material. That's what I said in the earlier case. If we have the two compounds there, one product is there, if that is stabilized enough, then only it will not go further. And that's what they have given in the second rule, that if we have functional group which are react twice, so it should be not, it should not go further. Now you see this one. So first step is that in order to synthesize the ester acid, ester chloride, they have chosen the alcohol and also the dichloroacetone. So in this case, what happens? It will, of course, the lone pair will attack at the carbonyl carbon, and this will go up, this comes back, and chlorine is departed. So in the first step, we get the COCl there. But this should be stable enough, because intermediate is stabilized. They have given not given the bar by. It can be by the stabilization of the intermediate can be by the hydrolysis or by the simple addition of water molecules there, so that the reaction further reaction can be stopped. So this is the case where the guideline 2 is given. Third is that it can be the problem of the above all cases can be solved by the protecting group. Of course, we know the protecting group is there. If we have the two different reactive groups in the starting material, then you can just protect one and make it unreactive, and then go for the second one. This was already we have discussed in the protection deprotection. So simple thing is that they have chosen the amino acid here to react with the, this is something like peptide bond formation. You see the peptide bond formation by using the DCC. So DCC is a kind of coupling reagent specifically used for the synthesis of amino acids or dipeptides. We can also say dipeptide. So first reaction is that this is the CBZ protection. Already we have seen the protection. CBZ protection can be done at the amine site, and you see the amine is now protected at the CBZ, and then the acid group which is present in the amino acid. Now you see amino acid is going to treat with the another amino acid. So one amino acid has to treat with the second amino acid, and we should get the product. Now the main problem in amino acid is that we have the basic compound, we have the acidic component. Now main problem is that if we treat this kind of species with the acid, what will happen? It will generate the salt at the nitrogen concentration. First problem is that. Second problem is that if we are treating with the base, what will happen? It will remove the acidic proton and it will generate the carboxylate ion. So salt from both sides, by treating with the acid or base, both sides the salt is generated. And once we know that salt are neutral in nature usually, तो उसके और न्यूट्रल रहता है, इसलिए उसका क्या होता है, रिएक्शन आगे करने के लिए प्रॉब्लम हो सकता है. देयर विल बी अ प्रॉब्लम इन द रिएक्शन. So the thing is that in order to make sure the sites for the, we just want to activate one side. जैसे यहाँ पे एसिड को हमको रिएक्ट करना था आगे वाले इसके साथ, अमीन के साथ, है ना, ये एसिड टू अमीन. तो इसके लिए उसको क्या किया, जो अदर पोर्शन अमीन का था उसको हमने प्रोटेक्ट कर दिया यहाँ पे. अगर इसको प्रोटेक्शन नहीं करते तो क्या होता था, इसी का एसिड दूसरे मॉलिक्यूल का, सेम मॉलिक्यूल का दूसरा अमीनो एसिड के साथ वो कपल होकर डायमर बनाएगा, है ना। तो ये भी प्रॉब्लम था वहाँ पे कि अगर दूसरे एक साइड से अमीन है, यहाँ पे भी अमीन था, so we have to protect it in such a way that the only acid goes to react with the amine functionality of the second amino acid, and then only it is possible to form the peptides. So this is the case where with amino acid we face the problem of selectivity, chemoselectivity. And of course, this is the state where later on under the hydrogen and palladium charcoal, we can just cleave the CB chain. So next is that one of the two identical groups react if the first is less reactive than the starting one. This is already we have discussed. Very similar pattern they have given. तो अगर वहाँ पे दो ग्रुप्स रहते हैं, देन जो पहला रहता है वो लेस रिएक्टिव रहेगा, जैसे यहाँ पे दिया है. नाउ दिस इज नाइट्रेशन, नाइट्रो ग्रुप, नाइट्रोबेंजीन treated with the similar condition for another nitration. So second nitration is there, and later on one of the group only. Now you see two groups are very similar, but they just want only one has to be reduced. So they cannot use lithium aluminum hydride. They cannot use platinum here, because what happens is that in the lithium aluminum hydride already we have the four hydrides. So it will two hydrides will go this side and two hydrides will go this side. If you, even though if you use the one molecule, and that is the problem, you cannot use lithium aluminum hydride. Even though you cannot use the metal, once you start using metals, what happens? It will not only activate this one, it will also activate this one, and that's why there is a special case here. So sodium thiohydride is specifically used where we have only one hydrogen there, hydride form hydrogen, and that is being used to activate the only one side, and this will be generated. And this is what the chemoselectivity. If we have the two similar groups, you can activate only one based on the specific or selective choose of the reagent where it contains the specific amount of hydride form of hydrogens. Next is that the fifth guideline, if the two groups are react with one equivalent of the reagent, then using the statistical effect. Yes, this is the same case I have already discussed here. If we can use only one equivalent here, something like this one. If we have one equivalent, then you can afford the one side product only. So the same case is appeared. You see dihydroxy group is there. By using the sodium in xylene, we can just deprotonate it and then attack on the ethyl bromide, it will generate the ether, only one product. So this has to be controlled by the statistical effect by using the equivalence. Next is that use a derivative of the होऊ शकतात ना. Now see, there are two cases. One is that if we label this is as 1 and this is as 2, just the label for the sake of product. So this may be 1, this may be 2, and this is 1 and this is 2. So there is a possibility of generation of other side also, but it will happen. Why? What happens is that if this sodium and xylene is removing this proton, and this will generate the oxygen minus at the two sides, right? Two number. 1 and 2 number is same. There is no reactive, no change in the properties, but the 1 number is becomes now OH. Try to understand this one. If you are removing one number hydroxyl proton, you will get this species. If we remove the second hydroxyl proton, you get this species. You see this species and this species, hypothetically both are same. And next step is that this will again go to attack at the same position and it will generate the same product. So the intermediate which is generating via control of the statistical effect is that the both the intermediates will be in the similar one. समझ में आ रहा है ऐश्वर्या? Are you getting my point? From this side also you are generating same intermediate. From this side also you are generating same intermediate. But the thing is that via the control of the equivalent of the sodium. Suppose something like the previously I said, if you are having only two molecules of this one, two molecules of starting material you have, and you want to change to the product. So one molecule will change to this one, other molecule will change to this one by the removal of both side hydrogen. क्योंकि एक टाइम पे एक ही हाइड्रोजन जाता है, ऐसा नहीं होता है कि ये दोनों साइड से एक ही टाइम पे निकालेगा. नो, दिस विल बी नॉट देयर. So one time only one hydrogen is removing, and that has to be controlled by the amount, how much amount we are adding in the reaction mixture, and that's what we can control it. And from this way we generate the both species very similar, and after the reaction with the electrophile we get the only one product, and this is how we can control it. Now is it clear? I think very yes. So the use of next is that the guidelines for the use of the having the two identical group which can react only once. जैसे एक ही बार उसको हम रिएक्ट करवा सकते हैं, जैसे इसे यहाँ भी देखा है, अगर एसिड के साथ करोगे, देखो यहाँ पे भी सेम कंडीशन है। उन्होंने क्या किया है, ओनली एक ही रूल है यहाँ पे, मुझे तो लग रहा है जस्ट वन और टू रूल्स ही है, बट दे हैव एक्सप्लेन द डिफरेंट वेज हाउ they have also explained with the nitro group, alcohols, acids, and previous case coupling one. So the four rule not should not be there. I think only one rule is there. We can begin then give the example with different functional groups. But anyway, just try to understand. So acylation is yeah, acetate per acetate है यहाँ पे. Actually acetate is yes per acetate, and now this acetate will generate the anhydride, cyclic anhydride. And by using methanol we can cleave it to form the corresponding only one side methyl group, and this is the way how we can control the methylation at only one side, and later on this can be used to convert in the other side also. तो यहाँ पे क्या बोलना है कि if we have a two same molecules we can make sure only one get reacted first and then second one get reacted by controlling the addition of specific reagents. Next concept is that regioselectivity. In regioselectivity we have the, of course we can have the one starting material and we can generate the intermediate, and later on the product which is generated will be the different one. And in regioselective reaction everybody knows that the main thing is that by using the condition where we can generate only one product will be generated in the predominantly. So major one will be only one product, and that kind of reactions we call it as a regioselective reaction. Even though there will be a possibility of generation of two products, three products, and also four products, five products are also there. But these kind of reactions will form only one, and that's what here they have shown. So this is simple one, simple methylation reaction, because of the two active sites are there. One is this one, other is this one. Under basic condition, this active methylene or the alpha proton can be removed, and this also can be removed. If it is removed from this side, this will get attacked and we get this product. And if it attacks from the opposite side, something like this one, the negative portion, and this will generate the R1 methylation compound. This is the difference. But the thing is that we just want only one. So how to deal with that one? The simple thing is that we can control the amount here. So now the example they have given for the alkylation of ketones. This is specifically for the alkylation of ketones. This is also alkylation of ketones. So we have the specific alpha hydrogen here that can be activated, and that's why it has been cleaved from this side. So after the cleavage of this one, this could be prepared from this kind of molecule where we can have the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, yes. And now we have the other side, here we can have the halide. So benzyl bromide is a very good source, so here we can have the commercially available. We can couple this together and we get this one. Then even though if you want this one also, again it can be cleaved from this side. And here this is the acetone. If we cleave this one, this is acetone and this is 3 carbon 1. So 1, 2, 3. And of course halide can be used. Something like substitution reaction. So in this one, first is that rather than use of the this kind of acetone, we can use the substituted one here, because here we have the positively charged, so ester is there. And by using the sodium salt of ethoxide, it will generate the this CC bond. And because after the this minus, यहाँ पे देखो propyl bromide, and this is also propyl bromide. So this minus will attack at the propyl side, where the carbon is having attached with the bromide, and bromide get departed, and we get the CC bond formation here. And next step is that of course one more hydrogen is also there, which is now more acidic in nature. Why? Because this is here we have the ketone, another ketone, but it's in the form of ester. So this 1,3 diketone, so the hydrogen which is present here, which flanked by the diketones. And if it is having the diketone, the acidity of this one is very high as compared to the terminal ones. So this one will get removed and we get the minus charge here. And this minus charge will attack at the benzene side, departure of bromine again. Here the first bromine is departed, second bromine is departed, we get the this kind of product. And finally decarboxylation, जो हमको पता है कि हम हाइड्रोलिसिस करके decarboxylation करने के बाद we get the target molecule. And you see this is the molecule where we are looking at to synthesize. Sometimes this also regioselective reactions are also comes under the Michael reaction condition, Michael condensation also. So Michael condensation where the alpha beta unsaturated ketones are usually used while treating with the nucleophiles. It will generate the two different products. So one is that it will attack at the 1,2 position if it is considered as 1, 2, 3, and this is 4. If it attacks at the 1,2 position, the carbonyl group get formed to get converted to form the alcohols. And if it attacks at the 1,4 position, this one the nucleophile will come at the 4th position. You see this is the 4th position. So usually whenever your Michael acceptor is this one where alpha beta unsaturated ketones is used, usually the 1,4 addition takes place there. So how we can deal with this kind of reaction? So if you want to synthesize, this is the target molecule now they have given, but it is in the cyclic form. So this one could be generated by via the cleavage of this CC bond. Why? Because this olefin is also there. This can be act as a negatively charged, and this can be act as a positively charged. And if you are having this one, the positively charged means what? We can keep the double bond there. You see. So this one, this two, this is 3rd position, and this is 4th. And now how we can deal with that one? So this the synthetic equivalence of this one is having the bromide. Once we have the negative charge there, it can be generated actually. It can be generated via the metal insertion. You know, metal insertion. जैसे metal insert होता है, this becomes negatively charged. And this is the now synthetic equivalence of recent cause. Next step is that this can attack on the alpha beta unsaturated cyclic ketone, and of course it will attack at the 4th position, and this is what the Michael reaction comes under, and then it will form the 4th substituted product. Later on this will comes back, and the enol generated will get protonated, and then it will form the product. Inertial selectivity, now this was about the regioselectivity. Now inertioselectivity, what we are dealing, we are forming a one enantiomer over the others predominantly, and via the same conditions. So here we have the benzyl group or the ketonic society which is attached to the aromatic ring. And here, of course, whenever you see a ketone, already we said there will be a possibility of two side attack. One is back side and one is front side. So there will be possibility of generation of two products usually. Ketone रहता है तो दो product रहते हैं. लेकिन यहाँ पे क्या हो रहा है? We are getting only one product with the 99% yield. You see 97% yield. And this is what? Only one enantiomer is generated predominantly, and this comes under the enantioselective reaction, because over the two enantiomer we are getting only one. Here also only one, because you see this is the stereochemistry is important here. By using the CPS, minus, if you use the minus one, the back side OH will form. If you use plus one, you will get the front side. You see the plus one, you get the front side there. So this one, here also we have the ketonic group, but by using plus you can get the front side. And this is the key factor here. By using the ligands, by using very less, you see 0.01 equivalent, by using the ligands which is specifically oriented in such a way that it will generate the specific compounds, and that's what it deals with the enantiomers. And you see this comes under the enantioselective. And finally, after the generation of this kind of moiety, it was used to form the final product. It climbed the company, and it would pressure, the blood pressure become blood pressure drug. This is the blood pressure drug they have synthesized via the by use of the enantioselective ligands, and we get the enantioselective products. Very famous reaction. This is always appeared in the next set also. They will one question will be always there 100%. So they will ask, they will give you the condition something like this one and plus one, and they will give you the options, four options there. So you have to make sure, try to remember this is allylic alcohol, sharply sour symmetric epoxidation. Always the allylic alcohol is treated with the titanium orthopropoxide or ortho isopropoxide, sorry, and tributanol in presence of diethyl tartarate. So this is the diethyl tartarate. So the stereochemistry of diethyl tartarate is based on the stereochemistry of hydroxyl group present at the 1,2 position. If it is in the front side, it comes as a plus. If it is at the back side, it is minus 1. Actually, plus and minus is also different concept based on the RR and SS also the orientation also we can consider. But now just try to understand how this plus and minus is changing the stereochemistry at the epoxide position. You see, this plus charge plus 1 will form the back side product, and this minus 1 will form the front side. How to remember it? There is one trick. You see the plus charge will have the two signs, one is left and one is vertical, one is horizontal. So what you do, these two lines you put it in the product, so it will be easy to remember how the product is generated, and based on this one you can recognize the product. And this is only one line, so one line only you can put it there, and that may be the dark line, and just connect this one, because this is the way how you can memorize the reactions. You have to connect somewhere in the reaction so that you can finally recognize the final products. And this is the way where enantiomer selectivity is there. You see, of course, rather than generation of mixture of products, it will generate the product with the one stereochemistry, with the one backside product or one front side product only. So by using the specific reagents, that's why Sharpless is very famous nowadays. Next is that enantiomer selectivity. We can also deal with the other kinds of products. So if this is the plus isomer which contains the front side methyl group, तो इसको कैसे लाना है, हम बैक साइड हाइड्रोजन जाता है ना, तो इसको कैसे ला सकते हैं हम? So whenever you see a molecule which contains the heteroatom there, you can either cleave from this side or either from this side. Now they have done from this side. So once this can be cleaved, this can be prepared via the this CH2 conversion to CH2. So there is two to three reactions. Two reactions. Clemenson condensation is there. Clemenson condensation or Wolff-Kishner, specifically Wolff-Kishner also, where the CH2 group can be transformed to CO group transformed to CH2. So this is first step. Yes, of course we can generate the amine by using amide one. Second is that you can break where from this side. कहाँ से ब्रेक किया? NH2, yes, this side. तो यहाँ से ब्रेक करने के बाद this whole portion will be the one side and this whole portion will be the other side. So this is tertiary butyl carbonyl chloride, and this is the substituted amine. And again this amine could be generated from the oxime. This is oxime now. So everywhere there will be some disconnection will be there, and this could be isolated or prepared from the phenyl toluene, methyl benzyl. So this one we can also disconnect here. You see, the oxime can be generated from the ketone. So ketone plus amino related reactions, we can get the product. So this is the first step now. You see, the ketone is reacted with the ammonium hydroxide, we get the oxime. So first step. Now the second step is very crucial, because in second step by using lithium aluminum hydride we are getting the expected stereochemistry which is required in the product, the backside hydrogen and front side methyl group. So this has to be resolved, because what happens if you don't resolve this one, because there is a possibility of generation of other product where the methyl group is present in the hydrogen is present in the front side and the methyl group present in the back side also. So resolution which should be there, resolution can be done by the HPLC also. So resolution is nothing but the separation of one isomer via the over the two, and उसका separation करके सिर्फ हमको यही चाहिए. तो यहाँ पे nature वाला we can isolate it, and then it can be treated with the benzyl tertiary butyl acid chloride. We get this kind of compound. And finally by using the reduction also, you see now the reduction is also there. Rather than using Wolff-Kishner or the Clemenson reduction, simply lithium aluminum hydride, the amide can be transformed to CH2. So we get the final target molecule. And this is also comes under enantiomer selectivity. Why this is enantiomer selective? Because we are controlling the specific stereoselective or stereospecific reaction in the inertia-selective way. Another is that there will be the one group CC disconnection with respect to alcohol. अगर alcohol का आपको एक group का disconnection करना है तो कैसे करोगे? Very simple. This is the alcohol where we have the CC bond is there, and this can be generated via the. Once you see the negative charge, of course, magnesium bromide will be there. If you see the positive one, you can either put the formaldehyde, and this can be generated. Of course, वहाँ पे तो ब्रोमीन चाहिए, तभी जाके मैग्नीशियम के साथ वो रिएक्ट करेगा. Yes, we have the bromine there reacted with the magnesium. Now this is the negative portion. You see, this is the negative portion which we are looking at here, and it will be reacted with the formaldehyde, very good electrophile, and it will generate. Formaldehyde is also very good source of 1CH2 group. You see, 1CH2 group. 2CH2 ग्रुप के लिए यूजुअली हम क्या करते हैं, इपॉक्साइड यूज करते हैं, बट एक CH2 ग्रुप के लिए कौन सा है सबसे बेस्ट रिएजेंट? CH2O, फॉर्माल्डिहाइड. तो ये सिंपल इसलिए है कि इसके ऊपर इलेक्ट्रोफिलिक सेंटर रहता है और न्यूक्लियोफाइल अटैक कर सकता है, एंड इट विल बी वेरी इजी टू जनरेट इट. You see this one 1, 2 and 3 carbon, but after the cleavage only 2 carbon is appeared here, and this 2 carbon is also appeared here. You see 1, 2, this 1, 2, and now this 1, 2 is come from the first one, and this is the CH2, the third one, the third carbon atom could be appeared by the reaction of formaldehyde only, and it is now there. तो इफ वी हैव कार्बोनिल स्पेसिफिकली रेडियो सेलेक्टिविटी अगर वहाँ पे देखना है तो हम व्हाट काइंड ऑफ रिएजेंट्स वी कैन यूज फॉर द फोटोसिंथेसिस. सो वन रूट इज दैट इफ वी हैव दिस वन हैविंग द कीटोनिक फॉस्फेट, इसको कैसे बना सकते हैं? ऑफ कोर्स वी कैन ब्रेक इट थ्रू दिस वन, और वाया दी दिस वन वी कैन मेक फ्रॉम द अल्कोहल्स टू द कीटोन्स. अब इस अल्कोहल्स को जैसे जैसे व्हेनेवर यू सी कंपाउंड वेयर वी हैव द अल्कोहल, biggest strength of Grignard is that it will generate the alcohol via various kinds of starting materials. So you can directly break it and make it to the Grignard one. And now other side we can just have the aldehyde. Same way magnesium, where the phenyl bromide is there, magnesium bromide will generate, and now this is the species. Now this is different species. So what we have to do, we just have to change the substituent in order to prepare the Grignard, and that's why the versatility of Grignard is there. It can be used for the various kinds of different reaction components, and it will generate the products, and that's why they got the Nobel Prize. So this is the reason. It is very versatile reaction. Again, if you want to get the alcohol, of course again Grignard, you see, either you can use from this side also and this side also. तो अगर इस साइड से निगेटिव करोगे तो जस्ट मिथाइल इथाइल मैग्नीशियम ब्रोमाइड यूज करना पड़ेगा, बिकॉज इथाइल कहाँ से आया है? यहाँ से आया है. And if you want from other side, of course it should be positive. So how positive can be? From the aldehydes. Very simple reaction. This again bromide, again Grignard, aldehyde के साथ react करेगा, we get the product. So once you understand the pattern of generation of negative charge and the positive charge, it's very easy to form the products. अल्काइलेशन ऑफ कीटोन्स, अगर कीटो स्टर इथाइल एसीटेट के साथ करेंगे तो कैसे हो सकता है ना? तो थ्रू दिस वन यू सी दिस इज द कीटोन बाय यूजिंग दिस फिनाइल बेंजील ब्रोमाइड. दिस इज बेंजील ब्रोमाइड नाउ, but here in this case what happens, they are getting a product where it will form the only CC bond, and the ketone is not getting formed. आ रहा है समझ में? यहाँ पे ऑक्सीडेशन नहीं हो रहा है, उसका ये रिडक्शन नहीं हो रहा है. So because of that one, you can see the starting material and the further reactions. How it can be generated? Usually the protection is there. You see, we have to protect the one side of the carbon atom by another group. और जैसे वो प्रोटेक्ट करोगे तो वहाँ पे जो नेगेटिव चार्ज कैसे बनेगा, यहाँ का जो अल्फा प्रोटॉन है निकल जाएगा, एंड देन दिस नेगेटिव चार्ज, दिस इज नॉट Grignard. Don't compare with the Grignard. This is not Grignard now. Phenyl bromide, benzyl bromide is an electrophile, and this negative portion is directly attacking at the carbon atom, and cleavage of bromine takes place. And later on, this can be cleaved in the form of carboxylate. अगर अल्कीन के साथ करोगे, if we are dealing with the one group disconnection via alkene, तो यहाँ पे ब्रेक करना पड़ेगा. अल्कीन को ब्रेक करो, तो अल्कीन को ब्रेक करने के बाद यूजुअली क्या बनता है ना? तो यूजुअली अल्डिहाइड भी बन सकता है, विटिक रिएक्शन भी कर सकते हैं वहाँ पे. यहाँ पे भी विटिक रिएक्शन है. Either if you don't want this one, you can use the cyclic ring में alkene बनाना है तो disulfide reaction. So if you in case of alkenes, one group CC disconnection we can follow the Wittig reaction. Wittig reaction is very famous reaction where it can be aldehydes or ketones can be treated with the phosphonium salt, and it will generate the product where it forms the double bond, and this is the double bond it generated. How the phosphonium salt can be generated? By the alkyl halide treatment with the TPS3, triphenyl phosphine. So it will generate the salt. This is the way. You see, triphenyl phosphine is reacted with the alkyl halide or aromatic alkyl halide, it will generate the salt. And now base is used. This is important. If you don't add the base, the proton which is present next to the phosphorus is not being removed, and once it is removed, then it will generate the double bond here. And this is the unique one, because in the target molecule we are getting the double bond and triphenyl phosphine oxide TPS3. If you look at the mechanism of Wittig reaction, triphenyl phosphonium oxide is a driving force, because generation of this one through the cyclic oxygen formation, what happens, it will generate the double bond one side and this will go in the phosphorus side. So try to understand the Wittig reaction. So via acetylenes also we can generate the alkenes. Why? How? Because acetylenes are the components where it can have the acidic proton, and that is the key role here. If we have the acidic proton, of course it can go to treat with the electrophiles, and this is the this also comes under the 1,1 disconnection. So this is the target molecule where we have the double bond, and this double bond, cis double bond, can be generated via the acetylenes. So triple bond conversion to the double bond is very good reactions. So if you use the Lindlar catalyst, this will convert the cis one only. And if you use the Birch reduction, it will convert the trans one. Try to understand what we have already learned so many days before, the conversion of acetylenes or the alkynes to the double bond. Now that concept is applied here. So via acetylenes, whether the alkenes is generated, one way is that of course Wittig reaction. Or other way is also there, we can generate via the Diels-Alder reaction. But there is another alternative. Yes, of course we can use alkynes. So how the reaction will be? The alpha proton will be removed by this ethoxide, negative charge will appear, and this will attack at this bromine first. So that this propargyl bromide, this is what we call propargyl bromide, is inserted at the alpha position. And now what happens? They have to protect this one. Now the protection deprotection strategy is applied. If you don't protect this one by using 1,2-diol, it will generate this kind of acetal product. And after the attack only, we can remove the acetylenic proton. This is the acetylenic proton here. And now NaNH2 is very specific for the removal of acetylenic proton. ये बहुत specific reagent है. सिर्फ वो क्या करेगा कि यहाँ का जो प्रोटॉन है उसको ही निकालता है. तो जैसे ही वो प्रोटॉन निकालेगा, then it will go to attack on the methyl iodide. तो मिथाइलेशन होता है. यहाँ पे आप NaOH कुछ नहीं यूज कर सकते. अगर आप NaOH करोगे ये ब्रेक हो जाएगा. आप K2CO3 यूज करोगे ये ब्रेक हो जाएगा. आप दूसरे बेसिस भी यूज करोगे ये ब्रेक कर देगा इसको. Because this protection can be hydrolyzed under basic condition, if you remember exactly, and that's why, of course this is a base, but this is not a base, it will go to react with this one, and that's why it is very specific to go to the other side, and this is the reason it has been used here. And now after the treatment of HCl and H2O, we can directly cleave it under basic condition also and under acidic condition also. And finally we get the hydrogen palladium charcoal, BaSO4. This is what Lindlar catalyst I was saying, Lindlar catalyst. So any position it is there, it will form only cis. You see the cis is there. Two hydrogens are present in the opposite side. So cis banana hai, so we must have to use the Lindlar one, Lindlar catalyst. Always remember this one. Write down somewhere in the notebook. Lindlar catalyst will always transform the alkynes into cis form, and Birch reduction will form the trans one. Now if you use the nitro compound and nitrile compound in synthesis, of course we have discussed that NH3 can become from the cyanide also, it can come from the alkyl halide, and this can become from the Friedel-Crafts reaction. So there is very simple routes can be applied in order to form the amines. Either amines can be come from the alkyl halide only, because we can do the amination also here. So there is also reaction, we can directly insert this amine. So rather than use of longer steps, you just use the one step. Next is that nitro compounds can be generated via the amines. So amine से amines can be generated from the nitro also, क्योंकि उसका simple reduction कर सकते हैं हम. एंड नाउ लेटर ऑन अगर सब्सटीट्यूटेड नाइट्रो ग्रुप भी बनाना है तो भी कर सकते हैं. किस कैसे करोगे? अल्डिहाइड का रिएक्शन मिथाइल नाइट्राइल के साथ करने के बाद. तो यहाँ पे वही रिएक्शन दिया है. नाउ तो नाइट्रो अल्केन का कैसे सिंथेसिस करोगे? तो यहाँ पे अमीन ग्रुप इज ऑल्सो देयर, वी हैव द फिनाइल. फिनाइल डजंट मैटर. तो अमीन कैसे लाना है? इट कैन बी जनरेटेड फ्रॉम द नाइट्रो एंड दिस रिंग कैन बी जनरेटेड वाया द डाइसल्फाइड रिएक्शन. एंड दिस स्पेसीज कैन बी जनरेटेड वाया दी फिनाइल विटिक रिएक्शन. यहाँ पे देखो विटिक रिएक्शन भी हो सकता है. तो फिर फिनाइल अल्डिहाइड और बेंजाल्डिहाइड ट्रीटेड विद दी मिथाइल नाइट्राइड. तो यहाँ पे देखो, यहाँ पे क्या है, डबल बॉन्ड बन रहा है. तो बट दिस वन इज ट्रांस वन. Now this one is treated with the disulfide reaction because we need to have the trans one. If we have the trans one, we have seen earlier case we get the trans chemistry, and this is what it is appeared. So the same concept can be applied in order to form the trans product, and later on double bond reduction करके we get the target compound. Very simple one. If we use the 1,3 dicarbonate, so far we have discussed the 1,2 dicarbonate. Now 1,3 dicarbonate. Let me see how much. Okay, we just take 5 minute break and then we'll come back.